AI bots that are in there.
Okay. So I'm going to share with you some recent work that me and my collaborators have done on a model that we call LLM Processes. So this work was done by myself and my co-first author, John Bronskill, who's on the call. He might pop in to answer any questions, as well as myself and Dami Choi, and our advisors, Richard Turner and David Duvino. David's also on the call too. So I think we might try and keep the talk hopefully pretty informal. So if you guys have any questions, please feel free to like pop in and ask or raise your hand, and I'll try and answer them on the spot. Okay, so first I'd like to talk a little bit about the motivation for this work. When we were doing this, we were hopefully trying to design a model that would allow us to make predictions by directly explaining to the model in plain language, in text, any information that the user might have about a particular problem. So, as machine learning practitioners, we know it's pretty difficult to communicate, say, priors to a model. You have to use very particular mathematical notation. Maybe you have to specify kernels or something like that if you're using GPs, and you try and like put all of your potential knowledge about the problem that you might have into this mathematical notation. It can be quite difficult, especially for a layperson. And so, the hope is to design a model that you can just say in words what you believe to be about a particular problem. We also like to harness the massive latent knowledge that we know is present in state-of-the-art LLMs. These huge models have been trained on massive amounts of data scraped from the internet. Like, they probably have insights into things that we're trying to do with our problems that the user themselves might not have. So how do we capture this information as well? And so our goal was to develop a model that we could do the following with. So suppose we have, some training points. We might call them training points or context points that we want to show the model. And we'd like to provide some guidance in plain language, maybe some information, maybe tell a little bit about the problem, and have it produce a probabilistic prediction for us that we can interpret visually. And so here's an example of what that would look like. So we could start typing a prompt to the model. We explain that it's a financial time series, so it's going to, move all of its mass above zero. We might say something like, okay, the stock price eventually, the company goes out of business, so it drops it to zero, and say like the stock actually explicitly goes to zero on day 30, and we could have the model actually condition on this instruction directly. So this is basically a picture of what, we want it to look like. We'd also like to do something like the following example. So in this spreadsheet here, I have housing prices for various houses across the United States, along with some potentially relevant features for those prices, like number of bedrooms and bathrooms, zip code, address, things like this. But some cells in my spreadsheet are missing, and I'd like to actually predict those values. So maybe I'm a real estate agent, I'm going to list the following houses, and I want to get some kind of prediction for what I can expect the houses to sell for. So one thing we could do is we could say, take all this information in the spreadsheet. We can construct prompts for our LLM that include all this information. And not only could we condition on the numerical values that are present in the spreadsheet, but we could include the text descriptions of these numerical values, as well as any text information that we might have. Like, we can explain the location actually directly, along with descriptors for all the numerical values. We could give this to an LLM, and we could expect it to give us predictions back, not only point estates, but hopefully some uncertainty about the prices as well. And then we could return these predictions to the user in the spreadsheet. So this would be like an automated push button way to just directly produce predictions from the spreadsheet directly. And so, you might be asking yourself, well, why would we think any of this would be possible? Well, there's been a lot of work looking at basically emergent abilities that have come out of LLMs when you scale these things to huge sizes. And basically, we've observed that as you make the model bigger and bigger, it can do more stuff. And framing the question like that is kind of a question about scale. Like, if I make my model larger, what can it actually learn? What can it now do? What are its new capabilities? But if we kind of turn this question in the other direction, we can view it about the language, or a question about what information is actually present in all the data that it's being trained on. With a sufficiently large enough model, is there actually information relevant to particular problems that we want to solve, like probabilistic regression problems that we want to solve in this use case, for example? So is that capability there with these large enough models, and can I actually access it with the type of thing that I'm trying to build here? And there's been some recent work on using LLMs for optimization, which gave us some inspiration. So this type of work basically uses an LLM. It prompts it by saying, look, I have this kind of optimization problem. Here's some like cold start points that I have. Can you give me some recommendations for what I should try next? And generally within a few iterations, they work very, very well, which, initially is quite surprising. And so we might ask ourselves under the hood, what is the LLM doing? Like, if it has the capability of actually solving these optimization problems, is it actually maintaining some sort of numerical prior about the problem that it's trying to solve? And can we access and examine them? And if so, if we're doing optimization, is it actually performing some sort of inference when we tell it new observations? Is it actually updating these priors in order to form some new posteriors? And again, can we actually like query them and look at them and maybe like poke at them visually? At the same time, there's been some recent work that has shown that LLMs have the capability to do time series modeling, probabilistic time series modeling. So there's a model called LLM time that came out, and it does it based completely on next token prediction. So you have a sequence of tokens, it predicts the next one, it gives you probabilistic prediction. And there's also been work that's shown that LLMs can improve on problems that are being asked of them by giving them context information that's relevant to that particular task. So we kind of had these two ideas in mind, and we wanted to like push farther on both of them and combine them. So in particular, with the time series prediction, we wanted to take this idea and we want to go beyond one-dimensional time series. We actually want to tackle multi-dimensional regression and density estimation. And to do this, we want to be able to condition on both data and unstructured text. So that was one of our main motivations for doing this. So before I go on, are there any questions? Again, I want to keep it quite informal. If you guys have anything to ask, please interrupt and let me know. So one of the big questions is, well, if we're trying to say, look at priors, look at posteriors, we want to examine whether LLMs have these things. How do we elicit a distribution over numerical values, given that, LLMs predictive distributions are probabilities over text tokens? Well, text is actually a quite flexible data modality, right? So you could imagine that, sure, it's outputting text, but in this text, it could actually be trying to encode like many different types of modalities. If we interpret it in different ways, it could be trying to do some kind of weird ASCII art, right? Or encoding an image, or like, it of course can like do essays, or maybe like some sound file. All of these things are possible just by like outputting text. And so if we want to actually elicit a predictive distribution from these things, we want to actually access like what we think are its beliefs about some numerical problem. We need to grab all of these potential sources of numerical predictions and kind of collect them together and use them to form our predictive distribution, right? And so obviously, like all these ones I've highlighted on the screen are all potential ways that the LLM could be communicating what it believes about a numerical problem. And I'm sorry, like I'm going to anthropomorphize LLMs because like that seems to be the only way to talk about them these days, but that's going to be a common theme throughout this talk. So in order to do this, I want us to keep two considerations in mind of how we could design our elicitation technique. So on one end of what I'm going to frame as a spectrum is the way I've been describing it is we want to develop a tool that actually examines the beliefs of the LLM, that actually like gets at the heart of what the LLM believes about a particular problem. And in order to do that, we're going to need to grab all sources of numerical information that the model could be trying to communicate with us. On the other end of the spectrum, we could say, well, I'm actually only trying to develop a rich prediction tool that I want to be well calibrated for problems. I don't really care what the beliefs are. I'm just going to throw this thing at numerical problems, and I want it to give me good results back. If I do that, that might be make things easier to elicit, because I can throw away a bunch of these sources. As long as I still have well-calibrated predictions, then that's all I care about. And so again, like I mentioned, if we want to be on the leftmost side of this spectrum, it's going to be a lot of work. It's going to be quite hard. We're going to have to like think about all possible ways that the model could be communicating numerical information to us about a particular problem. But if we start removing some of these potential sources, we're going to make our lives a little bit easier, but we might be moving a little bit away from the left-hand side of the spectrum. And so the method we're going to focus on in this work is probably the most obvious one initially, is just like, I'm going to assume that the model is communicating in decimal form the numerical predictions that it's trying to make. Now, there's a few things that I could do to maybe make the predictions better calibrated and make my life a little bit more easier. Like I could say, if I had a collection of data that I wanted to do a prediction on, I could treat this as a supervised problem, and I could do some fine tuning on my LLM. Now, this might eliminate some of the knowledge that the LLM has if we just treat it as a zero-shot problem. So this might move us a little bit more to the right of the spectrum. Or I can ask it to, like, give me a very specific form for its predictive distribution. I could say, like, tell me the parameters of a predictive distribution, like in particular, which again might be very, very easy to elicit, but might not capture all the different ways that it's trying to communicate its predictive distribution. I could also do some things that move me towards the other end of the spectrum, which we kind of did in our work, which is I could use some prompt engineering that sort of entices the model to place more of its mass on the form that I expect to see out of this thing. So, I could say, try and use a prompt to establish a pattern such that the LM would continue this pattern, and if it's trying to predict a particular numerical form, it's more likely that it will look like this in decimal form. So does that idea make sense to everybody? Cool. All right, so given that we're going to use standard decimal representation, we can say that we're going to expect numbers in that form, and we can start planning a rejection sampling strategy from eliciting predictions from an LLM. So suppose we have this type of data, we have some observations here, and we have some particular locations that we want to make predictions. The simplest thing that we could do is we could just convert these numerical values to a text prompt, just make them into a string, give the string to the LLM, and hope that the LLM continues this pattern, the pattern that I sent up using my string. And if I say, well, I'm only going to allow numerical values, I'm going to do rejection sampling, anything that's not a decimal representation, I'm going to throw away, and I'm just going to continue to sample it in this fashion. Then I can start forming trajectories for my predictive locations. So at each of these target locations, I'm doing this, I'm sampling one value using rejection sampling, and I can form this collection of trajectories, and I can use this to form an empirical distribution over the place that, over all the target locations that I'm trying to predict at. And so this works pretty well, but maybe we want to go beyond an empirical distribution. We want a more direct way of eliciting a predictive distribution. And if we want to do this, another method we could do is we could say, like, well, how do I compute the log prob of my model directly for a particular value? And for this, I could actually query the LLM's logits to compute the log probs. And I could say, well, I'm going to use a little bit of an abusive notation here, because I'm going to kind of like interchangeably talk about the integer numbers here and the token representations of those numbers in the LLM. But for the moment, let's just assume I want to compute the probability of the number 325. And using the autoregressive way that LLMs compute probabilities over text, I'm going to decompose this and say, well, this is going to be the probability of the first integer 3, and then the probability that the next integer is 2, given that the first one was 3, et cetera, et cetera, et cetera. And so I've just used the chain rule to break down my problem, and now I have to compute the probabilities of each of these components. And using this idea that I'm going to expect a decimal representation, I'm going to say, well, I can look at the log likelihood that my model gives to the number 3, and I can just normalize by using all of my allowed tokens. So the digits from 0 to 9, for example. And this should tell me my probability of that my first integer was the number 3. And I can interpret this as being the mass that my model assigns to all values that come between 300 and 400. And the reason that I can do this is because I know that any number that comes between 300 and 400 must start with this first integer 3. And I can continue down the line playing the same game. I can do the probability that my model assigns to 2 given 3, and then renormalized by my allowed tokens. Again, this is the mass that the model will assign to all values between 10, 20, and 30, given that the first digit was 3, or that we're in the 300ths place, and continue on. And this is, in fact, the method that LLM time, the using LLMs for time series work that I mentioned earlier, uses. It's kind of an elegant solution. And it matches up quite well, we would imagine, with just rejection sampling, because it's effectively the probabilistic version of rejection sampling and computing the log likelihoods and renormalizing by all of my allowed tokens. But it does have one problem that some of you might have observed already. If we now look at, well, I'm going to do the same method, and I'm going to look at what the probability of the number 3,254 is, I notice that necessarily the probability is going to be less than 325, regardless of any contextual information or the problem at hand. Just necessarily my model will assign a probability that's lower to this value. And the reason for this is because we need a way to establish an order of magnitude. So when I look at the integers 325, I don't know whether the model is trying to tell me 325 and we stop there, or 325 is the prefix for some number which is much longer than that. I need a way to establish that order of magnitude. Now, I'm certain there's lots of ways of solving this issue, but the one that we use in our method is we establish a terminal token via the prompt. So we basically selected a terminal token, and we say, okay, when the model outputs this terminal token, or when the terminal token occurs at the end of the integers, I now know that I'm done. I can assume that that was, in fact, the value that I want to compute the log prob of. But now I can no longer say that this matches exactly with the sampling procedure, because I can no longer say that computing 325 terminal token gives me the density that my model assigns between 325 and 326, because I've injected this terminal token in there. So, this raises a question, like how close to how close the distribution that this method elicits, how close to the sampling procedure distribution is it? Have I moved myself too far away from the true LLM distribution by using this method? So maybe that's a good place to stop. Are there any questions about that? Okay. So we asked ourselves this question, and we basically did some examples or some experiments where we looked at the predictive distribution under both the sampling procedure and this logit procedure that we're calling that the logit procedure. So on the figure on the left, the top is a heat map of the predictive distribution given by rejection sampling. The points in white are the observations, and the plot underneath is a visualization where we take the marginal predictions at X location, and we discretize the Y values, and we use the method that I just described to compute the log probs of all those Y values. And the figure on the right are visualizations of those marginalizations I just described at the white dotted line locations. So, we were asking the question, how far away from the sampling procedure does this logic-based method take us? And we were satisfied with the fact that our like visually inspecting it, it was pretty close. The distributions were pretty close. Injecting this terminal token didn't actually take us too far away. And again, I just
Sorry,
want to point. Yep.
I think we have a question.
Sure. Shoot.
Yes. So how do you measure here how distant the distributions are? Just KL or something else?
Well, you could look at the KL, and we in fact thought about doing that, but unfortunately, like we don't really have a way of grounding those values. So you could compute the KL between these two predicted distributions, and you'll get a number like 3, and then you'll say like, I guess that's close. I don't know, right? So like we thought about trying to do something numerically, but in fact, one point I want to highlight is we're not actually restricted to any particular predictive distribution. And the method that we just described here produces a valid predictive distribution. So it, in fact, like produces a predictive distribution given the LLM. So we're not breaking any rules. And we were just visually happy enough that we said, okay, like we think this is pretty close to the sampling distribution, and it is a valid predictive distribution, so we're going to roll with it. It's kind of how we treated it. I think there's another question.
Just a comment, James. Maybe there's a way of baselining that 3 by just empirically doing it with a diverse set of distributions, right? And then you could see whether it was even looking at that or not. So
yeah, that's a good that's a good point. I mean, yeah, or you could throw up some like other predictive distributions that you elicit from some other methods, and like, okay, if I use a GP, then my KL is this. Like, how far am I from this one or something like that? That's true. Yeah, I mean, if we were super concerned with like getting the exact same distribution, then probably we would have looked further. But we were sort of happy being like, okay, this kind of matches, and it's a valid distribution, so we're gonna say like it's pretty much telling us what the LLM wants to about the problem scenario. Yeah.
thank you.
Yeah, no problem. No problem. Okay, so we have a method for producing a marginal distribution, and we did a bunch of elicitation engineering to kind of get the highest quality predictive distribution we can to sort of like get, can we get actually good quality predictions from this? We used for all of these experiments open source models from Hugging Face. So at the time when we ran these experiments, we used Llama 2 and Mixtral mostly. So we examined prompt formatting. So we said, what's the best way of actually taking a data set and converting it to a text prompt to give to the LLM? And from the methods that we examined, we found that separating the x value, y value as a comma, and using a new line token as the terminal token struck a good balance between performance and token efficiency. I think it was one of the best performing methods, and it's relatively token efficient. And with a lot of these questions that we're going to be talking about in this talk, the answers come from empirical observations, so we're not really certain. But one hypothesis could be like this matches basically CSV formatting, which we assume like LLMs have seen a ton of, and so it makes sense that it would work relatively well. We looked at prompt ordering. So this question was: suppose we want to make a prediction at a particular target location, particular X value. How should we feed in the data, the training data, in context to the LLM? What order should it be in? And we found that we get a significant performance improvements if we rearrange the training data such that the points that are closest to our targets are last in the prompt. Again, we hypothesize that this is due to the whatever attention weights the model is giving. It places more attention on values which are closer to the token that's going to come next, so reordering helps. We looked at Y value scaling. So does it help, does it hurt to actually take our problem and to scale the values between particular values? LLM time does some Y value scaling for this very reason. We looked at this because we were hoping that it didn't actually affect performance, because we want to keep our y values in their native form in order to, so, part of the punchline is we want to later go to incorporating text. And we feel like if we are going to incorporate text, like say, this is going to be precipitation, and you've now scaled values to be negative, it might not work as well as if you just left them in their raw form. But unfortunately for that point, it does actually affect performance, but we found that it doesn't affect performance that much, but there definitely is an observable effect when you blow up your values, or when you add negative values, it does a little bit worse. And we examined top P and temperature for the predictive distributions, and it was surprisingly robust to varying these two parameters. All experiments, I should say, are obviously available in the paper if you want to check it out. Yep.
I had one question. What was the size of the XY value pairs that were inputted into the LLM? What is the maximum size?
What was the maximum XY value that we used?
No, maximum number of data points that you fed into the model.
So the maximum number of training points, effectively, is what you're asking.
Yeah, training points, yes.
So far, the maximum number of training points will be a function of your available memory, the token limit, obviously, and the number of features that you're going to be using. But in our experiments, I don't think we went beyond 100. John, is that correct?
Right. Yeah, most of the experiments in the paper kind of had between 100 or 200 training points. Also, the context window size of the LLM in particular is also a limiting factor, as well as just memory to store the activations along the way.
Yeah. Okay. Because one question I had, like just a deeper question on the next token prediction part. Is it actually calculating, or is it giving it a distribution of the next token? Because the number of training data points is just low. Because if you have higher number of training data points, then it actually has to iterate and then find a value. Or is it giving you based on the distribution of the next token prediction?
Oh, I'm sorry, I don't think I follow the question.
My question is, if it had, let's say, 20,000 data points or 100,000 data points, and the values of X and Y were more or less not in line with each other, then it would have to iteratively solve to find you the next predicted data point. And is it doing that, or it's giving you the next token prediction because of the lower number of data points supplied to the model?
Do you want me to take a stab at that, James?
Sure.
All we're doing is putting a sequence of XY's pairs in. Just pretend now there are 10 training points. So there's 10 XY pairs, and then we would want to predict at a location of, say, an 11th point, some other point either beyond the 10 training points or somewhere before or in between those set of training points. All we do is then put the prompt of the X location of the point that we want to predict for, and have the LLM predict the Y for that. And typically we would take multiple samples at each point. In the paper, we took, say, 50 samples. And so you get a empirical distribution with those samples at each new point that we want to predict.
Yeah, it sounds a bit like your question is about the way in which the LLM is solving the problem changing as a consequence of your context size increasing. And we didn't look in particular at any interpretability about what the LLM is doing. You just treated it as a black box, and we said, like, here's your context, here's your training points in context. Please tell me what the next Y value is effectively, and that's it.
Got it. Thank you.
No problem. I think there's another question.
Yes. Hi, James. Thank you for a great talk. First of all, it's nice to see something that goes beyond benchmarks. So, yeah.
Thank you.
And also, I think my question is that while experimenting with different models, did you see any difference between the instruction tune models and the general versions? Because recently there's been like a lot of investigation into what instruction tuning does for models. And I was wondering if you saw any impacts on your
Ye-
task.
Yeah, so unfortunately, like we were compute constrained, so we weren't able to run like strict ablations on questions like that. Like we definitely had them. Our approach was often like, let's use the biggest model at our disposal. But
Right.
we did in a couple of cases vary between instruction tuned and non-instruction tuned. I'm going to return. I'll return to actually because that's a big question. But to kind of give a bit of the punchline, surprisingly, LLM time. Well, not surprisingly, LLM time found that instruction tuning seemed to do worse when you're using your method for simple regression problems.
Okay.
We found, at least in the experiments that we run, that the instruction tuning seemed to help when you are incorporating text.
Okay. Okay. Makes
Um,
sense. And right. Yeah. And I had like a related question. And like, since these LLMs are basically trained on loads of text, and like, there's often been a question about the round number bias in these models. So they have most likely seen a lot more round numbers. So did you find that in your output space, was there like like a push towards generating round numbers for some reason?
yeah. So if you look at, so there's some heat maps in our paper where we discretized the predictive space, and we like looked at the log probs of all of them to form the predictive distribution, and they're definitely like artifacting, like say around 0 or around integers or things like that. So
Right.
yeah, there's definitely some of that going on.
Okay. Okay. Cool. Thank you so much.
No problem. Cool. Okay, so we've described a method for producing marginal predictions. So the question that we asked ourselves is, well, can we use these marginal predictions to define a joint distribution over our target locations? In particular, can that collection of joint distributions form a stochastic process? So what I mean by that is, let's say we have this collection of target locations, x1 to xn. We want to make predictions at y1 to yn. We want to form the joint distribution over those. A naive first idea that you could use is you could say, well, I'm just going to independently make predictions at each of these target locations, and I'm going to say that my joint distribution factors independently across all those predictions. And if I do that, then this collective of joint distributions satisfies Kolmogorov's extension theorem, which basically just says any collection of joint distributions that you have has to be permutation invariant in the target locations. So if I switch around my x values, I have to get the same joint distribution. This satisfies that trivially because they're independent. And also, if I marginalize out any collection of my target locations, I have to get the same distribution as if I just directly predicted that marginal distribution. Again, this naively satisfies that. So if you're interested in having a valid stochastic process, this indeed satisfies it. But we felt that there's a problem with this definition, which is that it doesn't give you rich joint structure between your predictions, right? If you're predicting them all independently. So is there a way to kind of use our construction to force some nice joint structure over our predictive distribution? And so what if we actually take our predictions, feed them back into our prompt, and iteratively produce predictions like this? So now explicitly we're forcing our model to condition on the previous prediction that it's made, inducing joint structure between our predictions. So if I write down the equation for this, this is the same idea that's done in any autoregressive model. I mean, this is copying how LLMs actually do their prediction. NAID, any density estimator, this is the trick they use. So this defines a nice rich joint predictive distribution, but then we ask ourselves, well, is this joint predictive, is this collection of joints actually a stochastic process? And on the face of it, the answer is no. Because now we have this dependence between the order in which we make our predictions. So technically, it's no longer a stochastic process. But we might ask ourselves, well, how far off is it, at least in terms of the question of permutation invariance? And so we looked at that. And we took a random collection of 10 ordering. So we ordered the target locations 10 different ways. And we looked at the predictive distribution. And then we looked at the log likelihood that we get as a consequence of that. And that's what's visualized here in blue. And we can see that, you know, relative to the ground truth log likelihood of the generative distribution. So we have a sample from generative distribution. The red dotted line is the ground truth log likelihood of that sample under our model. So relative to that, again, this question of like a baseline, that gives us a baseline. And we can see that the variance of any of these orderings is very small. So if you're, the punchline is, if you're a practitioner and you're saying like, I want to use the autoregressive one, but I don't want to get unlucky by choosing an ordering of my outputs because I might get a really bad prediction as a consequence of that. This is just some evidence to say, well, that's very unlikely to happen because the variance between your orderings, you get a much better predictive distribution by using autoregressive, and you're very unlikely to get unlucky with your ordering. There's another sorting question, which is if you have to choose the order of the predictions to make, one thing you could do is you could say, well, I'm going to predict first at the target location, which is closest to my training observations. It's sort of the reverse of that question I talked about earlier. And that's actually a pretty good idea. Those are the ones in circle, and generally that gives you better results as well. So I said a lot there. Is that clear? Cool. I think in the interest of time, I might skip over this. So we have some stuff in the paper which talks about neural processes. I have to shoehorn this in because this was like my PhD work. So I have to talk about neural processes. Neural processes are basically a model class which map directly from observations to predictive distributions. And that's what LLMPs are. They just, instead of being directly trained for this, we repurpose LLMs for this task exactly. So LLMPs are conditional neural processes. All right, so we've produced this method for eliciting joint predictive distributions out of LLMs. Are they any good? So we sort of asked, like, how good are they out of the box? If we just apply them to some synthetic data sets, you know, are they at all competitive, or do they just give us garbage? And, you know, we were quite surprised that they're very competitive out of the box with something like, you know, a GP. Here we look at a GP on these synthetic data sets, and they perform very competitively with it, which at the time, I feel like as more and more LLM capabilities come out, you're sort of like, yeah, of course, like, we know it could do that. But when we saw this, we were like, wow, this is pretty crazy that an LLM out of the box can keep up with a GP. We wanted to check its uncertainty calibration, so we used it for a black box optimization question where we explicitly like model the objective function. And so in this case, we have, you know, some synthetic function like this. We have some cold start examples, and we want to iteratively query the function to give us more information about the function in order to find the optimal value. So standard Bayesian optimization setup. And so we use the LLM as the model. It recommends using an acquisition function, which locations we should query next. And after a few iterations, we're actually able to get to the optimal value. And we compared it against Optuna, which is out of the box optimization package, and it performed as good or better, generally better than Optuna.
James?
Mm-hmm.
So somebody's asking in the chat if by GP you mean Gaussian process models.
Sorry, I do mean Gaussian process models, yes, indeed.
Awesome.
Yeah. And so, you know, again, the closest work to ours is LLM Time. LLM Time is a model, again, that produces, their predictive distribution is quite similar to ours, but they structure their data. It has to be sequential. They only input the Y observations as sort of a sequence of values, and then they ask the LLM to continue that pattern. so that they don't include any index information, they don't include any text, but we wanted an apples to apples comparison with LLM time to see like how our method compared to theirs. So we set up an experiment where we are predicting temperature for London on 86 consecutive days, starting on December 12th, 2023, which was important to us because that was after the training of the model. So we know that the model hasn't seen this data set in its training. LLM time then takes it and puts it in sequential ordering. It has a method for dealing with missing values. It basically imputes nans because it has to be a continuous pattern. So it just puts nans if anything's missing. Where LLMPs uses the index values for all of its observations. If something's missing, it's just not even included in the text prompt. And so we found out of the box better performance on this particular example from LLMPs. Its predictive uncertainty is visualized here. It does a lot better. And we found that as you remove more and more data, this trend continues that LLMPs perform better, potentially harnessing the information in the indexes, or potentially due to the one other difference is that they scale, as I mentioned earlier. They do have the scaling procedure. I'm not sure if that hinders performance at all. So we now have this way of producing predictive distributions using a text prompt. But as I mentioned earlier, one of the nice things about using text is it's very, very flexible. So with the text prompt, we no longer have to have one-dimensional data, one-dimensional inputs, one-dimensional outputs. We can actually have as many dimensional inputs or outputs as we want, and we can regress on any sub-collection of those things. So suppose you have some X values, some Y values. Some of them are observations, some of them aren't. All you have to do is you basically have to order your prompt such that all of your observed variables occur at the beginning and anything you want to regress on occurs at the end, and you go to town. And so it can handle that. And so we ran an experiment here where we have multi-dimensional output data. So we're trying to predict temperature, precipitation, and wind speed in London for these dates again. And we found that the LLMP using Mixtral outperformed the particular GP that we're using it on here. And again, to showcase the flexibility of this, we said, well, you can encode images in text prompts as well, and that's what we did. We took an image and we encoded it using its pixel location and its pixel intensity and a text prompt, removed a bunch of the observations, and got the LLMP to do image completion. Now, obviously, this is far from state of the art for this type of thing, but it's just kind of like a cool parlor trick that our method could do. And it shows like, yeah, you can stick images in, and anything you can encode in text, you could put into an LLMP and you could have it regress on, which is kind of neat. Okay, cool. So, so far we've shown that we can do like potentially as well as traditional methods, but there are obviously bespoke machine learning methods for each of the problems that I just described that will perform much better than this. Why would I go through all the trouble of building this on top of a big, expensive, slow LLM and use it for probabilistic prediction? Well, we believe that the big win is going to come when we start incorporating text information, the motivations that I initially said at the beginning. So going back to the CSV example, I mentioned that we can include the text descriptions of all the numerical values in the prompt. And so the question is, well, does that actually help? And so we ran an experiment again where we were trying to forecast housing prices for US cities using 10 training examples, which is a very small number of training examples with all those features. Case one, we gave the LLMP just the numerical values. In case two, we included the text information as well in the prompt as occurring right before the numerical value. So again, these have the same numerical information. We've only just added text descriptions and the location of the house in text as well, the city. That's the difference between case one and case two. And indeed, it helped quite a bit. So simply adding labels to the features improved the predictions and the uncertainty as well. You can see the predictions shrinking uncertainty shrinking around the true target and the mean value getting closer. Improved our metrics, so both mean absolute error and negative log likelihood got better when we include the text. So that's a really, really good sign in our opinion. So we know another trick that LLMs can do, which is to learn in context. And in fact, you can frame everything we did as in context learning because it's all zero shot. But we wanted to see if we show historical examples of the same task, can the model actually get better at performing that example? So we asked the model to predict monthly precipitation for different locations across Canada. We gave it 4 training examples, so 4 monthly observations, and we asked it to predict for the next 32 months. So it's quite a difficult task. So this is a visualization of exactly that. So we show it the 4 values in blue, and then we ask it to predict the remaining precipitation observations. You can see just zero shot like that. It kind of just gives you the average and sort of does okay. But then what we do is we give it between 1 and 10 historical observations of 36 months from the same location at some point previous in history. So we take 3 years from the past and we give that as in context information as well. And we can see providing this significantly improves predictions. So here's it being shown 1 historical example, 2, 3, and then around 4 it kind of nails it. So you can see, like, in cases where there's a really strong historical trend, it can pick up on it directly. When there's not really historical trend, it still does better. It kind of gets better at uncertainty because it's seen those historical observations. And the example that I showed earlier was a real example that we ran, showing it 2 data points and giving it a text prompt and asking it to forecast what will happen, giving this context information. But we also thought it would be interesting to take the exact same training points and just vary the scenario and see how the LLMP responds. So this was the financial time series, but we also took those 2 values. We queried its, like, quote unquote prior in this setting where we don't actually give it any text. And so there was a question earlier about the bias of the model. And we can see that does have a strong positive value bias if you don't give it any prompt. We then told it that these were observations from temperatures in Montreal starting in January. Moves the mass below 0, it knows that Montreal is freezing cold, and so it can do that. If we then instead tell it that it's in May, much warmer in May, so it produces much more realistic prediction, moves its mass now above 0. We did a side-by-side comparison with monthly precipitation in Singapore and San Diego, and I selected these locations because Singapore has one of the most flat monthly precipitation curves in the world, whereas San Diego has one of the strongest dependencies on month, so periodic structure. It knew that, it was able to recreate it. Okay, just a comment before we wrap up on limitations. So, LLMPs are built on top of LLMs, so they obviously inherit their drawbacks as well. So things like computation and context size limits, we're fighting against these things. As we're trying to use them, we're trying to apply them to bigger and more realistic problems, and we're coming up against these bottlenecks. It's just a reality of the situation. We're also limited in our research by open source models. And, just a comment about how, like, if this were to be widely applied, like any machine learning methods, there's the potential for abuse, like maybe consequences if you use this to forecast important stuff. And, the LLM it's a big black box. You don't know how it's making its predictions. There could be consequences from incorrect predictions and unknown biases lying in the LLMs as well. But on the other side of the coin, we're hoping that this kind of empowers everyday users to do probabilistic prediction, right? Like, as I mentioned at the very beginning, you no longer have to be an expert. You can now communicate your knowledge in text. You can access the knowledge that the LLM has directly. And so, yeah, that's one of the aspects that we're most excited about. And in the future, we'd like to see something where we're able to combine, multiple modalities, not just text and data, but say you have, text, images. So we want to do housing prediction. We can grab an image of the house. We can take the spreadsheet, maybe a video that the real estate agent has generated, and we can give it to an LLM, and then we can ask for its prediction on what the housing price should be. And we're not too far off from a pipeline like this. So moving forward, we've now shown in this work that we can connect LLMs to all of the work that's been done in probabilistic regression and joint distributions. So any of the tools for interpretation or analysis of those objects, we can now bring into this world, and we can we have another probe into and insight into belief. Again, I use the beliefs of LLMs. We can examine that, and we can also connect this into any existing pipelines that have as an input source like a predictive distribution, as we've shown with Bayesian optimization, for example. So any use cases that require a predictive distribution, you can now take an LMP and plug it directly in. And I think that this work justifies adding, predictive distributions as its own bespoke modality for LLMs. We've shown that the capability and the knowledge is there to produce reasonable predictive distributions. We've kind of developed a kludgy way of getting it out, but I think it justifies thinking a little bit more about actually having it directly output predictive distributions. And once we've done that, as I mentioned before, it flexibly mixes text and data and other modalities that LLMs can handle. And we can go beyond, we talked a little bit about putting text in and getting data out, but that pipeline can be reversed, right? We can have text data in, text data out. The world's our oyster. I think this is like the next step of what we'd like to look at. And so that's the end of my talk. But I'd love to hear if anyone has any more questions about any of the stuff that I discussed. Thanks for the emoji applause.
Thank you. So maybe I'll stop the recording just in case someone wants to ask a question without being recording.